Let's look at another problem. A couple things going on in this one. First of all, the notation is different. Our vectors here aren't given with capital letters with arrows over top or even bold capital letters, but simply the lowercase v with a subscript. Simply a different way to write a vector. And we're told what to do with vectors 1 and vectors 2 with this formula. We're told that the resultant is to be a sum of vectors 1 and 2. We're told vector 1 has a magnitude of 18.4 newtons. So this is a force vector. So a magnitude of 18.4, and it's directed at 202.4 degrees. So this is our first vector, not in quadrant 1. And as we'll see, the resultant isn't in quadrant 1 either. Let's draw a picture of vectors 1 and vector 2, with vector 2 being slightly shorter and directed at 65 degrees. So vector 1, given that it's at 202.4 degrees, must be in quadrant 3 if we draw it in standard position. And of course, vector 2, as discussed, is in quadrant 1, since it's directed at 65 degrees. Once again, I'll use the parallelogram method to draw the resultant of these two vectors. There we have the other two sides, it's a little bit rough, of the parallelogram, and the resultant is then the diagonal of the parallelogram, starting where the two tails of the original vectors meet. Of course, you could also have thought of this as picking up vector 2 and simply drawing it down here where vector 1 ended. The resultant is the same, whichever method you're using to think about it. I'll label this as vector r. Either lowercase or uppercase is fine here. We'll follow exactly the same steps. Even though the two vectors we're adding are not both in quadrant 1, the process is the same. We're going to find the x component of vector 1 and vector 2, add those x components up, and that will give us the x component of the resultant. We'll do exactly the same thing for the y components. Let's have a look. So vector 1 has an x component of 18.4 times the cosine of 202.4 degrees. And its y component will be 18.4, the magnitude of the vector, times the sine of its angle. So the sine of 202.4 degrees. Again, I'm just going to use this expression when I go to add the two vectors, but just to show you what those components look like, I have evaluated them. So the x component is negative 17.012 and the y component is negative 7.012. What's going on here? Well, we're in quadrant 3. So of course we're going to have to move in the negative direction along the x-axis and along the negative direction in the y-axis. It's the only way for us to end up in quadrant 3. All right, let's look at the second vector. So its magnitude was 16.6. We'll multiply that by the cosine of its angle, the cosine of 65 degrees. And not unexpectedly, that gives us a positive value. It's positive 7.015. And for the y component, we'll take 16.6, the magnitude, and multiply it by the sine of 65 degrees, which gives positive 15.045. All right, so now you're going to take 18.4 sine 202.4 and add 16.6 sine 65, hitting equals. To 3 decimal places, we get 8.033. Or you simply take negative 7.012 and add 15.045. But again, you don't necessarily need to take the time to write these down. Because we have a negative y component and a quite a bit larger positive y component for the second vector, the y component of a resultant is going to be, in magnitude, in between the two of them. And then for the x components, we end up with negative 9.997. Let's draw another quick sketch to draw only the resultant vector. So we had guessed, based on our sketch, that the resultant vector would be in quadrant 2, and the values we found for the components of the resultant confirm that. Since the x component since the x component of the resultant is negative, but the y component is positive, so the x component is negative, but the y component is positive, the resultant must be in quadrant 2. So the resultant will have an angle that is between 90 and 180 degrees. Let's label the x and the y components one more time. So negative 9.997 and then positive 8.033. So to finish this question, we need to fully describe the resultant, so we have to find both its magnitude and its direction. Let's start with its magnitude. So VR will be the square root of the x component squared plus the y component squared. So this time, because the x component is negative, I have to be careful to put that into brackets as I want to square the entire value. Or simply drop this negative because you know it's going to disappear once it's squared. In any case, that's the x component squared, and then I'll add the y component and square it as well. So the magnitude of the resultant to one decimal place, just to have it match the starting information, the given information, is 12.8. So that's the magnitude. Now for the direction. So the angle is going to be the inverse tangent of the components. Tangent is y over x, so being careful to write 0.33, the y component in the numerator, and 9.997 in the denominator. Notice here that I've just gone ahead and taken the absolute value of both the x and the y component. Or you could rewrite it and simply use the absolute value bars in there and indicate that at some point we knew the x component was negative. In any case, using the positive values or the positive and negative given values and absolute value bars, we calculate the theta, the value of theta, to be 38.783 degrees. I've left a couple additional decimal places here just so that I'm not rounding too soon. Now, is our resultant angle 38.783 degrees? Well, it can't be, because 38 degrees would be in quadrant 1. And our angle is not in quadrant 1. So what have we found? We found the reference angle. Remember that the reference angle is always up or down from the x-axis. So in this case, with our quadrant 2 angle, we know the resultant is in quadrant 2 with the negative x and the positive y components. So in this case, for our quadrant 2 angle, our resultant is up from the negative x-axis. So the measure in here is 38.783 degrees. That means that this is the reference angle, and our final answer for the value of the angle for our resultant is going to be 180 degrees minus 38.783, or 141.2 degrees. So to fully describe our resultant vector, we'd say that our resultant has a magnitude of 12.8. What are our units? Our units are newtons, directed at 141.2 degrees.